We always enjoy China. This picture was taken 7 years ago. So we feel whenever in China we are on top of the world. Well, now I am showing another example with Dr. Feng from Zhejiang. We have tested another example of another bradykinin neurotransmitter that is involved in blood-brain barrier permeability, and we have used B2 receptor blocker, a drug. And the idea is that this is a single compound, can also help. What you can see here, that this is the controlled blood-spinal cord barrier permeability. After injury it has increased. When we have given B2 receptor antagonist in lower doses, it has helped in reduction. This is neuronal nitric oxide synthase. It is also reduced. Blood flow is increased. So it's a good thing. But when the same drug is given in high doses, it has opposite effect. You can see here. All factors were adversely affected. So one has to see the timing, one has to see the doses. These are very important. And this is again the water content is reduced in right doses in both cases. Neuronal injury, in low doses it is very protective, but in high doses it is not protective. These are the example here, nitric oxide synthase, and after low doses you can see that the ventral spinal cord is also normal and you can't see much nitric oxide synthase level. Here is, you can see that low doses and high doses there were different results. So the drug doses and timing is also important. We always remember this is Dr. Feng. We were 4 years ago in Zhejiang. This is a nice Buddhist temple. And on some of the work, surprisingly though, Government of India has given us, this means Jewel of India Award in 2012. We are surprised anyway. And in this case, I am showing few results where you can predict the pathology of a spinal cord injury earlier than they develop using spinal cord evoked potential. What is important is this amplitude. I am showing this picture. If you can see, this is control. The amplitude is very fine. On the rostral side, after injury, they are all diminished. Those drugs that are able to reduce pathology, like PCPA, indomethacin, ibuprofen, and nimodipine, they preserve the loss of amplitude all. But all those drugs who could not prevent, like propranolol, phentolamine, dexamethasone, and cyproheptadine, this is the inverse result. This is at 2 to 10 minutes. So you can really see in 2 to 10 minutes which drug is doing better. But their effect on latencies are different, I'm not going into detail, I do not have time. And here you can see the same thing. Blood spinal cord barrier is also increased, and those drugs that were able to prevent the loss of amplitude were better. And this is same thing happening with water content and edema formation. I'm showing this picture again. Spinal cord injury, maximum swelling, PCPA, indomethacin, ibuprofen, nimodipine. They were able to prevent the swelling and edema, whereas all other drugs at 5 hours, cyproheptadine, dexamethasone, phentolamine, propranolol, they could not reduce the spinal cord pathology. So actually you can predict these changes very well. And again, the expression of CFOS is also reduced by some of these drugs. Lanthanum is not leaky when there is neuroprotection by these drugs, but the adverse drugs can produce more leakage here. So as the cell changes, those drugs, this PCPA, ibuprofen, they prevented changes. You can see here the untreated group, so much spaces, here they are not. And propranolol and cyproheptadine, they are not so well in protecting the neuropathy. This is an example of motor neuron. Here after indomethacin treatment, they are not that damaged as compared to here. So the point is that whenever we prevent the loss of negative amplitude, the edema is also prevented. And this is a very tight correlation between edema and loss of negative amplitude in a spinal cord injury. The final proof comes with here an example of myelin basic protein. You can see this is untreated spinal cord. You have even one side less swollen than the other because injury is one side. And this is a beautiful example of a spinal cord loss of myelin or axons. But here, after nimodipine treatment, you can see they are very well preserved. Even we can see that one side is slightly swollen than the other one. So this gives you a best example that how drugs can protect the spinal cord injury. These are at electron microscopy and nimodipine preventing in almost all cases. I'm not going in details. But what is the context of human situations? Are we going to the right direction? And this is the example we have used from our colleague, Professor Byron Kekulas from Perth, Australia. 6 hours after a spinal cord injury in human motor vehicle accident, you see leakage of albumin everywhere. And this is a very specific region, not overall, suggesting that whatever we see in animal situation, they are very similar in clinical cases. So we come to the conclusion here that whenever we try to prevent the leakage of blood spinal cord barrier, we can reduce cell death. In another 10 minutes, I will show you nano delivery of drugs. Is it okay? Yeah. So normally you label nanoparticles with liposome or soft nanoparticles to deliver the drug. And sometimes these carbon nanotubes are also used for labeling of the drug. But as I have shown you, there are different or thousands of things are released after injury. How can we treat with one single? It's very difficult. At least they can be active for short term, but cannot have any solution for long term. So we have to look for a drug that should be a combination. Either we have a cocktail of drug, or there should be a manufactured company that should produce different drugs together, a balanced combination. So cerebrolysin is one of them because it is also helping in neuronal survival, neuroprotection, neuroplasticity, and even neurogenesis. All these factors are very important for neuroprotection. And this comes in form of liquid, so you have to inject in doses in milliliter. 2.5 or 5 milliliter per kilogram is the standard dose. It has clinical trial in the United States, China, Asia, and in many other countries. In Europe, these are some of our basic research publications with this drug. So we have used titanium nanowire done by Professor Ryan Tian and Dr. Wang in United States. And these are the transmission example of nanowires. These are the study, they are studying cell culture, but we are working on in vivo situations. These are the way that either we can enhance this drug transport at the blood-brain barrier, but particularly when there is an injury, the drug can penetrate, particularly if they are labeled with nanoparticles. So there are two aspects I am showing you. This is the same model that we are making a lesion, and as I told you earlier, that when our soldiers are inflicted with silica dust, the question is whether they have more pathological changes after identical injury. My answer is yes. This is the untreated, means normal spinal cord injury, and this is after silica treatment. You yourself see that the pathology is much more higher. This is the example where you can see cell loss is almost complete. Whole spinal cord is spongy after silica intoxication, and here without silica intoxication. Also the barrier after silica intoxication is higher, so as the edema. So the first point is that when you have nanoparticle intoxication and then you get the injury, you have more damage. So these damages cannot be cured by the drug in normal doses. We have to find a solution to enhance its delivery. So we are using this titanium nanowire to deliver the drug. The question is, was asked also in your lab before, that can we label every drug? The answer is yes, but whether if we just label 3 or 4 drugs, all could become good? My answer is no. Each drug, depending on its own property, can have better effects. But a bad drug cannot become good if you level with nanowire. That is my answer. So here you can see that this is uninjured edema here in T9 and T12. A good drug is given after 5 minutes, is producing good result. But if the same is given after 1 hour, there is good result, but there is a difference. So time is also very important. The same is true with leakage of iodine here. See, 5 minutes after and 1 hour after. This is in T12, the same result, and this is the control level. This is the same result after 5 minutes and 1 hour. So what we can say, that even the good drug given at right time have maximum neuroprotective ability. Another question is, we have leveled different drugs, for example, 2, and given at different time periods, 5, 1 hour, 3 hour, 5 hour. Depending on the timing, the best time is given 5 to 10 minutes after. It can reduce the lobe scale function, it means improve motor function as compared to this is completely normal and this is untreated. This is an example telling that we have three different drugs have labeled. The best drug is still one that is also showing better result, but it is extended a bit more. If it is not nano labeled, normal drug is given, then the picture will be like this. So if you have given with nanowire delivery and the drug is good, it is acting for longer time and better. This is an analysis telling which drug is better side. There are 4 compartments. This is the most damaged compartment and this is the most normal. Here you can see some of the drug. The best drug is here in the almost near normal compartment, but some of the drugs are in between. It means that nanowiring of different drug can produce different effect, but even much better than without nanowiring. This is the same in high magnification. And another example to prove my point that this is untreated and this is nanowire treated. You can see here that they are much better than this situation. Also at light microscopy these neurons are damaged, but here they are very well preserved. On the basis of these works, Brain Edema Association in Tokyo, Japan has given us this American Neurosurgeon Award who worked whole life on blood-brain barrier in edema and brain injury. So we feel that we are encouraged. Then I just show you some work of my master thesis student in Uppsala University. She did also this spinal cord injury and leakage of albumin after different types of nanoparticles treatment. So here is silver and copper and this is the normal. So the leakage is enhanced. So as the neuronal injury is enhanced after nanoparticle intoxication as compared to the untreated group. And in this case, when we have given cerebrolizin, here, this is silver plus cerebrolizin. And when we have given nanowire cerebrolizin, you can see the result is much better than the cerebrolizin alone. This is also nanowire cerebrolizin in silver and as compared to the copper. So the point is that if you have a good drug and you are delivering through nanotechnologies, you can get a still better result. However, we have to work more. Again, some example that those drugs are doing better. The leakage cannot be seen. And this amplitude is also recovered when we have given nanowire cerebrolizin here as compared to the untreated group. However, the latency could not increase even the nanowire cerebrolizin was given. These are some examples that CFOS expression is also reduced by nanowire cerebrolizin. C-Jun is also reduced after nanowire cerebrolizin. And these are the edema changes. You see that nanowire cerebrolizin has the best effect in T12 and T9 level. Again, cerebrolizin given with nanowire, this is very clean spinal cord. And the situation is also here that edema is very well preserved. This picture is very interesting for you. You have seen the untreated picture. This is indomethacin, normal, no nanowire, but see cerebrolizin treated after nanowiring, the myelin is much better preserved. The basic cause of these preservation is probably they are reducing stress at the cellular level. So here the stress protein measured as heat shock protein is completely absent or very little is expressed as compared to the untreated group. So again, if we are reducing these phages or gene expression by any drug, we can also able to reduce cell death. And in this all investigations, our former Prime Minister of Sweden, Göran Persson, is helping us very much. We are very grateful. And there are various organizations supporting our research, including Pharma, Case Western Reserve University, Swedish Strategic Forskning Research, the hospital, Beijing Hospital in Shijiazhuang, and many other organizations. It's a long list of supporting group and organizations. We are very grateful to them. These are our partners at different places in the world. And here I stop to listen to your comments and questions. Thank you very much for your kind attention.
Thank you very much, Dr. Sharma, for very nice. Now it's time for the questions.
Yes.
Thank you very much, and it's excellent presentation. I'm very interested in the, so you said using nanomaterial to culture the mouse embryonic stem cells, right?
Yes.
So, and your the results, and you showed, and because we know that to culture the mouse embryonic stem cells, we need the cell layer. So we normally use the mouse embryonic fibroblast as a cell layer. You use the nanomaterials,
yes,
right? And you reported that, and that the nanomaterials can increase actually growth of the mouse embryonic stem cells. But you use the cancer cells, and then that nanomaterials can inhibit the growth of cancer cells.
Yeah.
So what the mechanism?
Yeah, it's very fine.
Yeah.
You see, if these nanowires are targeted in the cell culture towards particular cancer cells, they can kill. They will penetrate into the cell and kill the basic neuronal nucleus or other mechanisms. By this, they are inhibiting the growth. But this thing cannot happen in normal cells. Probably there are different kinds of nuclear membrane or something like that. This is so far is the hypothesis. We don't know the real mechanism yet. But when the whole cells are growing on the nanowires, the situation is entirely different. So they are growing better because they feel better environment, and probably some other toxic or other effects may not be that strong. So these are the reasons that they are growing on the nanowires, and the nanowires, when used to kill the cancer cells, they are penetrating particular cancer cells because of they might be different. But still the whole mechanisms we still do not know. These are only observations.
So for the mouse the embryonic stem cells, and if we use nanomaterials, so it's not necessary to use mat cells as the feed layer cells.
We are not experts of the stem cells. These are only observations that how nanowires can interact with biological materials.
Mm-hmm.
So maybe it is open for others to do more experiments and find with some other facts. These are only known to us.
One more question. I'm very interested in that the cerebral lysine.
Yes.
And the reporting. So for that it's a nanomaterial drug, right?
No, this is a normal drug. You have to nanowire. Any drug is normal. You have to combine with either nanowires or nanomaterials to get delivered the nanodrug. There no nanodrug comes in its own.
So that is combination of a variety of growth factors.
Yes.
Okay.
So you mean actually when you mentioned the different effects of nanoparticles on the cancer cell and the normal cell. So you mean with the normal cell, the nanoparticle also internalized, or?
No, the effect of nanoparticles on normal cells and disease cells are different, at least in cell cultures. And also, different nanoparticles may have different effects. So far, the silica nanowires and titanium nanowires are used to kill cancer cells in cell culture. There are also some other reports research in the literature. But not so much study has been done on other kinds of nanowire cells. So any effect of the nanowires or nanoparticles depend on its material, its size, its diameter, because my wife has presented a paper in Society for Neuroscience that came in big news that size and age dependent neurotoxicity of nanomaterials. If the animals are of different ages and you use the same nanoparticles with different sizes, the smaller size is more dangerous. The larger size are not that neurotoxic, and also the age. The younger and older are more susceptible to neurotoxicity than the middle-aged group. So there are many factors. Also the charge of nanoparticles influence if they are negatively charged or positively charged. So this is a whole new area, and we have to understand much more better its neuroanatomy, neurotoxicity, and physiology.
So the question, when you use the same, let's see, the same particle, same size, same material, with the nanoparticle, do you see the difference effect on the?
Yes, so far we are using a particular diameter of nanomaterials, 50 to 60, 20 to 30, and 90 to 120. We have not gone beyond that. And 50 to 60 is most neurotoxic if they are used as a nanoparticle as such. When we have, so far the nanowiring material, we are using only 20 to 30 nanometer of titanium nanowire. And if we give titanium nanowire itself, no drug, then by itself it did not induce neurotoxicity. This is the most innocuous in vivo situation. And then we level the drugs with this titanium nanowire. The drug effects are enhanced. So these are all fine. But this is a lot to do in this area.
Any questions?